morning students, and welcome back to your chemistry class. So in the last few videos we had done Aufbau's rule. We also have finished Pauli's exclusion principle. Today we are going to discuss about what is Hund's rule, and further we are also going to learn today how to do the electronic configuration. So what did Hund state about the electronic configuration? He stated that pairing of electron spin will start only and only when all the orbitals corresponding to a given azimuthal quantum number of an energy state, they are singly occupied. Clear? So let me first write it down for you, and then through examples I will explain and it will be clear to you. So Hund's rule stated that pairing of electron spin will start only when all the orbitals corresponding to a given azimuthal quantum number of an energy state are singly occupied. Okay, so at large it means to say that first the orbitals, the degenerate orbitals, they have to be singly occupied. When all the orbitals are singly occupied, then only the pairing of the electron will start, right? So through examples I will explain you this. So over here Hund's rule is also called as principle of minimum pairing and maximum multiplicity. Okay, multiplicity. So Hund's rule is also called as principle of minimum pairing and maximum multiplicity. Now let us understand what does this particular Hund's rule state. Now Hund's rule, it provides guidelines of filling of the electrons in the degenerate orbitals, okay, of an atom. So now we have come across a new word. What is that? Degenerate orbitals. So what do we mean by this degenerate orbitals? They mean the orbitals having equal energies. Okay, they are termed also as degenerate orbitals. So over here, if the number of electron is equal to or less than the number of degenerate orbitals, then the orbitals are always singly occupied. So let us take one example. Suppose like there are 3 electrons, right, to be filled in p subshell. Clear? Now if we are talking about p subshell, that means it has 3 orbitals. What are they? Px, Py and Pz. Clear? This is Px, Py and Pz. Now these are termed as degenerate orbitals. Why? Because these orbitals, they have equal energy. So they are degenerate orbitals. Now what was the first thing that I said over here? That if the number of electron, it is equal or less than the degenerate orbitals, right, then what will happen? The electrons will be singly occupied. So what are the number of electrons I have given you? 3. So over here there are 3 degenerate orbitals, so singly they will be occupied like this. Fine. If somebody is thinking of it can be occupied like this, then it is wrong. Py and Pz, and this part is wrong. This cannot happen. First, all the orbitals have to be filled up singly, and then only we can go for the spinning of the electron. So this is wrong and this is the right method. Okay. Now, suppose there are 4 electrons, right, to be filled in this Px, Py, Pz. Then in that case, what will happen? If there are 4 electrons, now 4 electrons means more than the degenerate orbitals. Now the pairing of the electron spinning will take place. Okay. So over here, how are we going to show? Px, Py and Pz. There are 4 electrons. So 1, 2, 3. And then comes the 4th one. I hope this is clear. This is very clear to all of you. This way it will be wrong. If you think of filling up the orbitals like this, then this is wrong. This is the wrong way. First it has to be completed singly in all the 3 orbitals, and then we move to the first one. So this was the Hund's rule. I hope this is very clear to all of you. Now, since we know Pauli's exclusion principle, we have understood of Bohr's rule and Hund's rule, we now move to do the electronic configuration of certain elements. Electronic configuration. So let's learn how to do electronic configuration. I'm going to do few of them for you. Rest you are going to practice on your own how to do the electronic configuration. More you practice, more it becomes easy for you. So let us begin with the first element, that is lithium. Atomic number is what? 3. Configurate 1s2, 2s1, 2 and 1, 3. Clear? Then let's take another one, nitrogen with atomic number 7. It will be what? 1s2, 2s2, 2p3. Then we come to neon 10, 1s2, 2s2, 2p6. So 6, 7, 8, 9, 10. This is neon, completely filled. Okay, noble gas configuration it shows. Next, sodium, atomic number 11. So 1s2, 2s2, 2p6, 3s1. Okay, then next let's talk about aluminium, atomic number 13. 1s2, 2s2, 2p6, 3s2, 3p1. Then let's take argon. Argon atomic number is 18. So 1s2, 2s2, 2p6, 3s2, then 3p6, right? Then let's talk about manganese. Atomic number of manganese is 25. So 1s2, 2s2, 2p6, 3s2, 3p6. This gives you 18. Okay. Then 3d5, 4s2, 18, 20, 25. Clear? Then next we come to say silver. Silver atomic number is 47. So let's configure this also. Then 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s1. Let's see this. 10, okay, 10, 20, 30, 40, 46, 47, 47. Then let's come to xenon. Its atomic number is 54. So this becomes what? 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, then 5s2, 5p6. So till 4d10. Okay, so let us total this. 10, 20, 30, 40, 40, 54. This becomes your xenon. Okay, let's take one more. Barium. Barium atomic number is 56. Okay, so let's do the configuration of it. 1s2, 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6, 4d10, 5s2, 5p6, 6s2. So I hope you have understood how to do the electronic configuration. Now I will teach you how to learn the condensed form of electronic configuration. See, it is such a long way to write this. So there is an easy method also to write down this electronic configuration, that is the condensed form of electronic configuration. So what is condensed form of electronic configuration? For convenience of writing and saving space, the condensed electronic configuration method is to be followed, right? Over here in this type of configuration, the outermost electrons, or you may say the valence shell electrons, they are only shown in the orbitals, and the electrons of the other orbitals, or the inner ones, they are shown in terms of symbols of the preceding noble gas configuration, and they have to be written in the square bracket. So till neon, so everything has to be shown. Neon becomes your noble gas. So let us observe the condensed formula from sodium. So I'm going to put a slash over here and write down the condensed formula for each one of them. So for sodium, if you check 1s2, 2s2, 2p6, this follows neon. So I can write it down neon in the bracket like this, and the last shell can be written as 3s1. So this can also be the configuration of sodium, that is neon 3s1. When we say neon, means we say that 1s2, 2s2, 2p6, that is 10 plus 1 makes it 11. Now let's talk about aluminium. Aluminium also, it has 10, right? So we can write over here neon and then 3s2, 3p1. So 10, 12, 13. 13 becomes the atomic number. Now talking about argon. Argon itself is your noble gas, but this also can all be written in the condensed form. How? Now this is your 1s2, 2s2, 2p6. What is this? This is neon. So this can be written as neon over here, and then 3s2, 3p6. This becomes your configuration for argon. Now let us talk about manganese. Now in manganese, you see, this is for neon. Okay. Then till here 3s2, 3p6, that makes it 18, is argon. So now you will not write neon and argon. Instead we have reached till argon. So how are we going to write this? We write here argon. So when we write argon, we have already understood that 18 electrons are there. What is left? 3d5, 4s2. So 18, 19, 20 and 5, 25. Clear? Look over here for silver. This is what? Neon. Okay. Till 3p6, what is this? This is your argon. Now further, Now look at this till here. This is 18, 18 and 20, 36. 36 is what? Krypton. 36 is krypton, so we can write here krypton 4d10 5s1. Okay, now this is xenon. How to write down for xenon? This much is your neon. From here to here you have reached for argon. From here to 4p6 you have reached krypton. So you can write over here also, it is krypton till where? 4p6, right? And then 4d10 5s2 5p6. Clear how to write down the condensed electronic configuration? Let's write it down for barium. Now for barium, how much do we know? Till 4ps we know that this much is what? Your krypton. So 4ps till here it is your krypton. Okay. Now further, another one is xenon. Xenon is 54. So till where? 5p6. Do we have 5p6? Yes. So till here we have reached where? Xenon. So the condensed formula of barium will be what? Xenon 6s2. I hope you have understood how to write down the Aufbau's rule over here for the electronic configuration, and also have understood how to write down the condensed formula. So over here, to write down the condensed formula, what is very important? To know the atomic numbers of different noble gases. Like for example, I am writing it down over here for you so that you learn it. Neon, it is 10. Then argon, argon is 18. Then is your krypton. Krypton is 36. Then after that is your xenon. Xenon is 54. Similarly, you have radon. Radon is your 86, and so on. So if you remember this, then only you can easily write down the condensed formula. I hope writing down electronic configuration is very clear to everybody. Okay. Our next topic is stability of half-filled and completely filled orbitals. Now, what do we mean by stability of half-filled and completely filled orbitals? There are certain elements which show certain deviation in the electronic configuration based on Aufbau's rule. Okay. So when the orbitals, they are half filled or completely filled, then they show more stability. Then they show more stability. Do you understand this point? When the orbitals, they are either half filled or completely filled, then they show more stability. And this stability, what does it depend upon? It depends upon two reasons. The first reason is the symmetrical distribution of electrons, and second point is the exchange energy. Clear? All these points you will come to know as I proceed with my explanation. So firstly, let us understand what do we mean by half-filled and completely filled orbitals. When I say half-filled, look over here. I mean to say, suppose I take p orbitals. Okay, this is px, py and pz. So if I say it is half filled, here I am showing you half filled orbital. Okay, and here I am going to show you px, py, pz completely filled orbitals. Okay, so what do we mean by half filled? When there is just one electron in the orbital, in the degenerate orbitals, then it is said to be showing symmetrical distribution of electrons, right? And hence it shows stability also. Is this point clear? Now, let me make you understand what do we mean by completely filled orbitals. Over here, completely filled orbitals means this kind of orbital in which the two electrons are present and they are completely filled. Then also they show symmetry of the electrons and hence it is said to be stable. Hence we say what? Half filled orbital or completely filled orbital, they are stable due to their symmetrical distribution of electrons. I hope this is very clear. The exchange energy I will explain you while giving you an example. So, there are certain elements which show certain deviation from the Aufbau's principle. Okay, so let us take few examples over here. Like for example, chromium. Chromium, the atomic number is 24. So let us go ahead with the Aufbau's principle first to show the electronic configuration of chromium, and then we will come to this part of stability of half filled and completely filled orbitals. So let us configure this according to Aufbau's principle, that is 1s2, 2s2, 2p6, 3s2, 3p6, 3d4, 4s2. Okay, now let's check this. 10, 20 and 4, 24. So this is the configuration given for chromium by the Aufbau's principle. I hope this is clear. Now write it down in a condensed form. So how will we write down in the condensed form? See here, this is 10, 18. 18 means argon. This much is what? Argon. So we write down argon 3d4, 4s2. Okay, now one thing I would like to explain you over here. This half filled and completely filled orbitals, the stability and their stability, I am talking about which subshells are going to show this. They are going to be shown by P, D and F subshells preferably. Okay, why not S? Because S orbital, if it has one electron, then it is half filled. If it has double electron, then it is completely filled. So in both the case, the S orbital has no issue, right? It is always going to show stability, right? What is more important about the stability of half filled and completely filled orbital is of P, D and F orbitals. Okay, so now let us see and understand. Let me draw 3D over here. D means how many orbitals to be present? 5. So 1, 2, 3, 4 and 5. And this is 4s2. 4s2. So now 3D, 4. 1 according to Hund's rule. 1, 2, 3, 4. And this is 4s2. Now check whether they show half filled or completely filled orbital. This is your D orbital, this is your S orbital. Now D orbital, it is not half filled because this orbital has no electron over here. So we can say this is an unstable configuration. The configuration that has been given by Aufbau's rule for chromium is unstable. That is what I said in the beginning, that there are certain elements which show certain deviation from Aufbau's principle. I hope this is very clear. So now how it is going to become stable? By showing half filled orbitals. So what can be done? If we take away one electron from the S orbital, what will happen? S orbital still will be half filled and it will be stable, and it is also going to help the 3D orbital also to get stable. So instead of this, what are we going to do then? 1 2 3 4, this becomes 1 1 2 3 4 5. Okay, so now your configuration becomes what? This configuration is argon 3d5, 1 2 3 4 5 and 4s1. This is more stable. This is more stable than argon 3d4 4s2. I hope this is very clear. One point is clear. Why? Because now this d orbital, it shows half filled orbitals, therefore it is stable, and s is obviously half filled, so it will be stable. Now I would like to, so this shows a symmetrical distribution of electron. So this is one point why it is stable. Secondly, I come to exchange energy. Now let us talk about exchange energy. When two or more electrons with the parallel spins, they are present in degenerate orbitals of the subshell, they tend to exchange their position. They tend to exchange their position. It is somewhat like when two friends, when you are friend in the school, then you maintain certain distance, but when you become too friendly, you are true friends, then you start moving to each other's house and you become familiar with each and everything, and you become more stable. Your friendship becomes more stable. Okay, so over here also, the exchange of energy, more the exchange of energy, more moving from one orbital to another, there will be more exchange of energy, it will show more stability. So let us see in case of the configuration that is given by Aufbau, why this does not show stability. Let us see the energy exchange. So look at the first electron. First electron can move to one orbit, then it can go here also, it can go here also. Okay, so 1 2 3, this is vacant, it will not go here. So first electron moves how many? 3 places. So energy, exchange energy for first electron is 3. Let's talk about the second electron. It is 1 and 2. So 2. For the third one, it is only 1. So how many? 6. Are you getting my point over here? So what did we see over here? The total exchange of energy in this particular configuration is how much? 6. Now let us talk about this. First electron can move to 1, 2, 3 and 4. So 4. Let's talk about the second electron. 1, 2, 3, 3. Third one, 1, 2, 2. And the fourth one to 1 place. So 4, 4, 8, 9, 10. Over here, what did you see? The total exchange of energy is 10. And here it is only 6. So where there is more exchange of energy? In this particular configuration. Hence we say this is the correct configuration of chromium. So do not blindly write down the configuration, only check by this method whether it follows the stability of half filled and completely filled orbital theory or not. If not, then your configuration is wrong, and if yes, then it is correct. So I hope chromium example is understood by you. Lastly, I come to another example of copper. Now, copper atomic number is 29. Okay, so I write down the configuration. Let's write 29. 1s2, 2s2, 2p6, 3s2, 3p6, 3d9, 4s2. Okay, so let's check. This is 10. Okay, 20 and 9, 29. Okay, write down the compressed electronic configuration of copper. What it will become? It will become till here. It is what? Argon. So we write down argon. Okay, 3d 9 4s2. This is the configuration of copper according to Aufbau's principle, right? Now let us draw and observe. This is for 4s2. 3d. D means how many orbitals? 5. 1, 2, 3, 4, 5. It's 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. This. So do you think it will be stable? Firstly, the symmetrical distribution of electron is not there. Look at the last orbital. And now talk about the exchange energy. This will be also less than what will we see next. If one electron from here s orbital comes to this side, then it will be more stable. So in that case, 1, 2, 3, 4. If this is 1 and it gives away one electron to this side, so what does it become? See, now this is completely filled orbital, right? And this is half filled. So this is more stable than this one. So if this is more stable, then what should be the electronic configuration? It should be argon, then 3d, how much? 10, 4s1. So this is the deviation from the Aufbau's rule, which follows the stability of half filled and completely filled orbital. So with this, we wind up with the chapter also, and tomorrow I shall come up with more of the questions based on your 4 quantum numbers, your principles, that is Hund's rule, and your Aufbau's principle. I will also ask you to do certain electronic configurations, and we will also come across certain unique elements which are going to show the stability of half filled and completely filled orbital theory. Thank you.